Hello, I am Justin Lacey of Team 6, and I'll be presenting the AL Solutions metal dust explosion and fire that occurred on December 9th, 2010. AL Solutions is a production and processing company that is based in West Virginia. They work to collect aluminum and zirconium scrap from other manufacturers and recycle it into pressed compacts to be used by clients as alloy additives to increase the strength and protect other metals from oxidation. Alloys are used in everything from buildings to automobiles to surgeries and much more. Although AL Solutions is integral to society, they have failed multiple times to maintain a safe environment for their employees. The most notable of these incidents is the dust explosion at their New Cumberland location on December 9th, 2010. Three operators were fatally injured, and a contractor was wounded in the blast. Zirconium and titanium are both highly flammable and pyrophoric. Because of this, they need to be considered a major ignition source, and the company should have taken them into account more severely in their risk analysis and risk management processes. The table shown is of the U.S. Chemical Safety and Hazard Investigation Board's analysis on the severity of the materials in question. Pmax, or maximum pressure, is the greatest amount of pressure and maximum amount of damage that the dust can cause in a confined space, while Kst is the dust constant. Maximum explosion pressure can be independent from the size of the vessel, but the rate of the explosion pressure cannot be. Because of this, the larger the vessel, the lower the maximum rate of pressure rise will be. The constants are given classifications based on the range they are in. For both zirconium and titanium, they fall within the range of 1 to 200 bar meters per second. This classifies them as ST1s, or weak explosions. During the incident, two operators were on presses and another was working the blender. The blender's metal blades struck the metal wall, causing an ignition source and ignited the zirconium inside. Zirconium dust cloud wafted into the air and exploded. This ignited all the storage drums filled with titanium and zirconium, leading to extensive damage. Leading up to this incident, safety requirements such as closing the lids of the blender, storage drums, and hydraulic presses whenever possible, keeping material not in production in a separate warehouse, and industrial hygiene practices were never reinforced by management. This resulted in a non-existent safety culture, and in addition to this, when the blender started to make metal-on-metal contact, management only went as far as enacting short-term solutions like replacing parts or readjusting the blades instead of readjusting the entire blender or replacing the entire blender. The USCSB created a model of the process that led to the explosion, which I will now play.
As the metals were broken down during milling, the risk of a metal dust fire or explosion increased as the metal particles decreased in size. A metal blender used to process zirconium was having mechanical problems that had not been adequately repaired. As a result, the blender was producing heat or sparks due to metal-to-metal contact. Around 1:20 p.m. on December 9, 2010, a spark or hotspot from the blender likely ignited the zirconium powder inside. The resulting flash fire lofted the metal dust particles in the blender, forming a burning metal dust cloud. The cloud ignited other combustible dust within the production building, causing a secondary explosion that ripped through the plant, killing 3 workers and injuring a contract employee.
Dust explosions require 5 things: fuel, an oxidizer, the suspension of the dust particles, the confinement of the dust particles, and the source of ignition. The removal of either the suspension or confinement element can prevent an explosion, but that won't prevent a dust fire from occurring. The titanium and zirconium acted as fuel in the situation, with air being the oxidizer, while the metal blender took up the role of confinement, suspension, and the ignition source. The heat from the metal-on-metal contact in the blender created the ignition for the first explosion. This ignition source would have been completely non-existent had the blender been properly maintained. The explosion inside of the blender, assuming that the blender had a capacity of 6,000 liters, or 6 meters cubed, can be modeled using the equation shown. In our case, the only variable that cannot be easily assumed from the environments was the volume. Because of this, we had to assume a basis for the size of the blender. This basis was decided by the industrial-sized metal blenders found during our research for the cost analysis. The energy outputted in this explosion was estimated to be around 56.8 kilojoules. This is equivalent to around 13.6 grams of TNT. For the secondary explosion, the confinement and suspension changed to the blending process room inside of the building, and the source of ignition is now the previous explosion. The ignition in the blender evaporated the water inside, kicking up the zirconium particles, creating the conditions for the secondary explosion. Now, to estimate the volume of the inside of the building for our formula, we went back to the video that the USCSB created. A standard door in the US is 36 inches wide and 80 inches tall. Using this information, we can estimate the building's exterior to be 504 inches wide and 192 inches tall. That can also be stated as 12.8 meters wide and 4.88 meters tall. Using that information, along with the floor plan included in the CSB's report, we can determine the size of the room for our estimation. This calculation comes about to give us a volume of 1,550 meters cubed. Going back to the equation we used previously, we can keep the assumptions based off the environmental surroundings and change only the volume. This change will give us a new energy output of 14,673 kilojoules. This amount of energy is equivalent to 3.51 kilograms of TNT. As a result of this incident, AL Solutions lost 3 employees causing pollution to the environment, damaged the blender, a forklift, the process feed conveyor, and part of the facility. They also had to pay a $100,000 fine in settlement to the US and paid another 17.5 million to settle wrongful death claims, and also lost money having to hold production for a period of time. This this amounted to significant losses that could have been avoided if proper long-term solutions had been introduced to their system. The introduction of a dust collection system, recommended by industry standards, would manage the dust without adding water to the facility and causing the accumulation of hydrogen if a fire occurred. Installing ventilation for hydrogen would also be beneficial, although with the previously mentioned system, it wouldn't be a priority. Another change would have been to add Class D fire extinguishers in the event that a metal fire did occur. Each extinguisher is about $824 at a Fire and Safety Plus and similar sellers. The procedure at the time of the incident was simply to evacuate, call the fire department, and wait out the fire. This procedure leads to an increase in extended fires and explosions. While the extinguisher can lessen the extent of the damage and save money overall, the most important change would be to replace the whole blender with a new one and get rid of the source of ignition. These are fairly expensive options, however. The most cost-efficient strategy they could have enforced was the safety requirements and a good safety culture. If this were done, then the damage would have been contained to just the blender and wouldn't have had any casualties. Sadly though, AL Solution never has had a good record when it comes to workplace safety. Besides the 2010 incident we discussed, AL Solutions has had two other incidents in which workers were fatally injured, and in a time period of 10 years, they had 7 other fires that were severe enough to the point where the fire department had to be called in to handle them. As chemical engineers, we have a responsibility of understanding risk and protecting others as well as the environment by complying to strict safety guidelines and leading by example. We take a code to do no harm, and we must take that seriously for the overall betterment of ourselves and society. Learning from the mistakes of others can help us do that. This case study is dedicated to the 3 men who lost their lives as a result of the AL Solutions incident on December 9th, 2010. James Eugene Fish, Jeffrey Scott Fish, and Steve Swain. Thank you for listening.